what's up? Faizan here from Research Beast. On this channel, I share different tips and tricks for researchers, different motivational talks, and I also talk to experts about the research methods or anything related to research. So if you're interested in content like this, please consider subscribing to the channel.
Hello everybody. So, just like the theory development methodology also needs to develop, and many of us use quantitative analysis or quantitative analytical techniques. One of them that is very prominent is partially squares. Now, traditionally, we have all been using things like reflective constructs, formative constructs, and stuff like this. However, recently we saw an increase in discussion about confirmatory composite analysis, which is about composite constructs. The problem is that there's not a lot of literature available on this particular concept, and how do we use this concept in our research. So confirmatory composite analysis is basically a subtype of structural equation modeling that deals with composite models or composite constructs. Today, it's my pleasure to have Dr. Florian, who is an assistant professor in the University of Twente in Netherlands, to talk to us about composite confirmatory analysis. He is one of the leading scholars who are discussing the CCA in detail. He has done several good papers about CCA, the concept, how do we define it, how do we apply it, and all that type of stuff. So without further ado, just stay tuned. My quick talk with Dr. Florian is coming up next. Just make sure that you watch the whole talk, because we'll talk about CCA, the concept, the theoretical aspects of CCA, and then later Florian will also talk about how do you apply it with a proper example and data, and how do you analyze the models using the data for CCA. So stay tuned, the video is coming up next. So Florian, thank you very much for taking my invitation to speak about CCA, because you are one of the few people who started talking about it, and some of your papers were very interesting, very good to lead people into this direction. So thank you again for taking the invitation and coming here and talking about confirmatory composite analysis, what it is and how it is applied. The floor is all yours.
Yeah, thank you, Faizan, for the invitation and the nice welcoming. So yes, of course, also welcome everybody who's watching the video. As Faizan said, today I will present confirmatory composite analysis as developed by me and my co-authors, Jörg Henseler and Theo Dijkstra. And I will show you what it is and how it is applied. So here's a brief structure of my talk today. So first I will tell a little bit about the background of CCA. And then in the second half, I will present the steps of CCA, and I will also give a brief demonstration of CCA, so how it is applied. So before we start with the history of CCA, I of course want to briefly introduce myself. So those who don't know me yet, my name is Florian Schuberth. I studied business administration economics in my bachelor's at the University of Würzburg in Germany. And subsequently, I did my master's in economics at the same university. And then I did my PhD in econometrics under the supervision of Martin Kuckuck and Jörg Henseler, which I finished in 2017. And then looking for a position in academia, I fortunately found a position as assistant professor at the chair of Jörg Henseler at the University of Twente, where I'm still employed. So that was a little bit to my background. And now we can come to the history of CCA. So to my knowledge, CCA was first mentioned in an article of Henseler et al. 2014, which was a response to a critical paper of Mikko Rönke and Jörg Evermann about PLS. And in that paper, they presented CCA as an approach to assess the overall model fit of a composite model. And in their footnote, or in the author footnote, there they highlighted that the idea of CCA belongs to the first co-authors, which was Jörg Henseler and Theo Dijkstra at that time. So that was, to my knowledge, the first paper that mentioned CCA. Of course, it was not fully elaborated at that point of time, because the motivation of the paper was to provide an answer to all the critiques raised by Mikko Rönke and Jörg Evermann. Then in 2018, finally we got a paper published. So I published it together with Jörg Henseler and Theo Dijkstra in Frontiers of Psychology, and which was the first full elaboration of that approach. And then in 2020, together with Jörg, we introduced CCA also to business research in the Journal of Business Research. So yes, at that point, before we come to the actual steps of CCA, I want to briefly thank Theo Dijkstra and commemorate him. Unfortunately, or sadly, he passed away last month, and his ideas were substantial to the development of CCA. So a lot of his ideas influenced CCA and goes back to him. So therefore, I wanted to commemorate him and give him a special thanks at that place. Okay, then we can come to confirmatory composite analysis, what it is and how do the steps look like. So CCA is an approach to structural equation modeling, and as common in structural equation modeling, it consists of 4 steps. So step 1 is specifying the model. Step 2 is making sure that the model is identified. Then in step 3, we need to estimate the model parameters. And in the last step, we assess the model. And I will go through all these steps now in more detail. So let's start with step 1, the model specification. So what does model specification actually mean? So typically in explanatory statistical modeling, we have a theory from which we think that it describes the world. So here we have the theoretical model, which links theoretical concepts to each other. And then researchers usually also have an idea about how the theoretical concepts are linked to the observable variables. Here are represented by x1, x2, and y1, y2. So this takes place in the plane of theory, so to say, so in our mind. And then if we want to assess a theory, we need to convert our theoretical model into a statistical model. So this you can see here in the lower part. And there we have different ways to do so. And to my opinion, the way how to model a theoretic or a concept depends on the type of concept. So let's have a look at different types of concepts. So to my understanding, there are at least 2 types. So the first type of concept are theoretical concepts, or also often called behavioral concepts. So these are called behavioral concepts because they often occur in the realm of behavioral sciences. And what we think about these concepts is that they exist in nature, regardless of whether we measure them or not, but we cannot directly observe them. And therefore, we want to measure them because they exist. So therefore we can measure them. And the statistical pendant, so to say, is the reflective measurement model, which uses a latent variable in the statistical model to represent the theoretical concept. So the eta here is the latent variable, which represents our theoretical concept. And then we have linear relationships from our latent variable to the observable variables. And then we have the epsilons, which represents measurement error. So I guess this model is well known. So this is the classical reflective measurement model. And examples of theoretical concepts are attitudes or traits. And the dominant statistical approach to assess theoretical concepts is confirmatory factor analysis. So this is, I think, quite clear. Next to the theoretical concepts, I argue that there are also forged concepts. So these are concepts that do not exist in nature per se, but they are constructed by the researcher or designed by the researcher. So for example, capabilities or values. So values can be defined. We will also see that later in the example that I've chosen. And therefore, yeah, measurement theory or the reflective measurement model seems to me not a good choice to operationalize such forged concepts. Because the reflective measurement model ignores the designery aspect of forged concepts, so that they are constructed or designed. And what we proposed in CCA is that you should use the composite model to operationalize such concepts, meaning that the concept is represented by an emergent variable instead of a latent variable. And moreover, the relationship between the observable variables and the emergent variable is rather a definitorial one than a causal one. So we say, okay, y1 to y3, they define, they construct the concept, or in that case, the construct, and do not cause them. And yeah, the statistical approach to assess forged concepts is confirmatory composite analysis. And as you will see later on in my presentation, CCA is quite similar to CFA, but the only difference is the model that we take into account. So we don't consider a reflective measurement model, we consider a composite model, which comprises an emergent variable instead of a latent variable. So here's also a brief decision tree how to decide which way of operationalization shall a researcher use. So I borrowed that from a book that of Jörg Henseler that will be published soon at the end of the year. So if you think that the theoretical concept exists and you can measure it and you want to measure it, then employ a latent variable to represent it in the statistical model and specify a reflective measurement model. Or if you think you face a forged concept, so a concept that emerges out of its ingredients, components, then employ an emergent variable, a statistical entity, and specify a composite model. So hopefully that helps researchers to decide how to model a specific concept. Then I have also prepared a small composite model. So here we have x1 and x2, they together form the emergent variable eta. So here the comp or the emergent variable with its components, it's highlighted by this dash box. And then the emergent variable is also embedded in a nomological net, so to say, represented by y and z. So these are two other observable variables. And this is, yeah, a very simple composite model, but yeah, it's sufficient for my purposes now. And what we can see here is that the x1, x2, the two components of the emergent variables, are allowed to be freely correlated. So there are no restrictions on the correlations among the two observable variables. And yeah, then we also allow the emergent variable to be freely correlated with y and z, and similar for the correlation between y and z. So how does the model implied variance covariance matrix looks like? So I wanted to keep it as less technical as possible, but I mean this matrix is important to explain the concept of step 2 model identification. So therefore I briefly wanted to show it. So what is the model implied variance covariance matrix? So this is the matrix between our observable variables implied by our model. So let's have a look. So here on the main diagonal, we have the variances of our observable variables. So sigma yy, sigma 1, sigma 2, sigma z. So this is the variance of z, variance of x2, variance of x1, variance of y. So that's easy so far. Then we have here in the next row, we have the covariance between x1 and y. And as you can see, this is implied by the model through lambda 1 times the covariance between y and eta, where lambda 1 is the covariance between x1 and the emergent variable. So let's have a quick look at the model again. So what we are interested in is the covariance between y and x1. So how is that covariance implied by the model, or how does it look like? So it is this covariance times the covariance between the emergent variable and x1. So this is simply written here. So lambda is the covariance between x1 and the emergent variable, and sigma y eta is the covariance between y and the emergent variable. Similar can be done for the covariance between x2 and y. And then we have the covariance between y and z. So as we can see here, we have no restrictions on it, therefore it's simply sigma y z. And then here we have the covariance between x1, x2. As I mentioned before, we put no restrictions on that covariance, therefore it's again sigma 1, 2, as you can see here. Then we have the covariances between z and x1, x2. So again, covariance between x1 and the emergent variable times the covariance between the emergent variable and z. Similar can be derived for x2. Then we come up with these two values. So this is how the model implied variance covariance matrix looks like. Okay, so why is it important to know how the model implied variance covariance matrix looks like? Because it facilitates the understanding of model identification, about which I'm going to talk now. So step 2 is a researcher needs to ensure that his or her model is identified. So what does that mean? So as you've seen before, the composite model depends on a set of model parameters. So actually these are the weights which are comprised in the composite loadings lambda. Then we have the covariances between the components forming an emergent variable, and we have the covariances between the emergent variable. Oh, there's a mistake, it should be an eta. I can update that later. So between the emergent variable and the other two observable variables in the model. So we have a set of model parameters, and model identification means that we can uniquely retrieve the model parameters from the variance covariance matrix of the observable variables, which you can see here on the right-hand side. So what does it mean? As you can see, we have 10 equations. So what we do is we set each element of the one matrix equal to the element of the other matrix. And then what we want to do is we want to solve that set of equations with regard to the model parameters, and we want to figure out, is there a unique solution? So that seems to be quite complex now, but imagine you have an equation which says A times B equals 1. Right? As you can see now, there's an infinite number of values for A and B that satisfy the equation. So yeah, A can be 2, B can be 1/2, for example, both can be 1, and so on. So there's an infinite number of values, then we have no unique solution. But if I add a second equation, for example, saying A equals 1, then I have two equations, A times B equals 1 and A equals 1, then it's clear that B must be equal to 1 and our model would be identified. So this here is the same logic, just a little bit more complex. So we want to ensure that we can uniquely retrieve the model parameters from our variance covariance matrix of the observable variables. Fortunately, model identification is quite straightforward in CCA. So actually we need only two rules. The first rule is we need to fix the scale of the emergent variable. So those of you who are familiar with CFA, there we have the same problem, right? So we need to fix the scale of the latent variable. So in CFA, this is either done by fixing the variance of the latent variable to a certain value, typically to 1, or fixing one of the loadings of the indicators to a specific value, also usually to 1. The same applies here. So we also need to provide a scale for the emergent variable, and that can be done by either fixing the variance of the emergent variable to a specific value. For example, here is the emergent variable, and we fix it to 1. Then we fix the scale of the emergent variable. Another alternative approach would be to set one weight to a specific value. That can also be done, but then of course the variance of the emergent variable is not 1 anymore, and then we have no standardized parameters. So therefore, typically researchers use that approach. And this is also what is done automatically in PLS. So if you use PLS, then all the composites have a variance of 1 by default, because PLS ensures that the weights are scaled in such a way that the variance of the created composites is equal to 1. So therefore, we've solved the first condition, or satisfied the first condition. Second condition is each emergent variable must be connected to at least one other variable not forming the emergent variable. So if we have a look at our previous model here, so here we have our emergent variable, and it's not enough that it's connected to x1 or to x2 because these components form the emergent variable. A necessary condition is that the emergent variable is also connected to another variable, in our case here, y or z. So this is the second condition for model identification. And then, of course, if we embed the emergent variables in a structural model, which is not part of CCA, then we also need to ensure that the structural model is identified. So therefore, I put it in brackets because it's actually not part, but for completeness. And if the two conditions are satisfied, then we can retrieve all the model parameters from the variance covariance matrix of the indicators. So as I showed you before. So here I also presented a small example of a composite model that is not identified. So imagine we have an emergent variable that is formed by x1, x2. And here we have 3 parameters, w1, w2, and sigma 1, 2. And let's assume we know the variance covariance matrix so we can avoid the Greeks. And we set the correlation between x1 and x2 to 0.5. And now we also ensure that the weights or that the emergent variable or that the scale of the emergent variable is fixed. So we set it to 1. So the first condition is satisfied. Then we still have a problem because our emergent variable is isolated. And as a consequence, as you can see, there's an infinite number of weight sets that satisfy the scaling condition of the emergent variable. So for example, if I choose two weights or set the 2 weights to 0.58, then I obtain an emergent variable with a variance of 1. Similar, if I set them to 0.38 and 0.76, then I also obtain an emergent variable with a variance of 1. And these are just 2 examples. There's an infinite number of weight sets that satisfy the scaling condition. So therefore, it's important if you use CA that your emergent variable is embedded in a nomological net, or in other words, not isolated. Then we already come to the third step. So once we ensure that the model is identified, we come to step 3, model estimation. So what does model estimation mean? So typically the population parameters, here I call them zeta, are unknown. So zeta comprises the weights and the correlation between the components, the correlation between the emergent variable and other variables in the model. So these are typically unknown because we have not complete access, so to say, to the population. So usually in empirical research, we only have a sample. And then with the help of the sample, we want to estimate those parameters. So this is the purpose of model estimation in general. And of course, then the sample needs to fulfill certain requirements. For example, it should be representative of the considered or studied population, because otherwise we come to wrong conclusions. Okay, so now we have a small issue. What shall we do? Or what type or which estimator shall we choose to estimate our model? And in statistics, estimators are categorized with regard to the properties they have. So the most, two well-known properties, I would say, are consistency and unbiasedness of an estimator. And I will just briefly explain, because I mentioned them often in my papers, and I'm not sure whether applied researchers often fully understand what these two concepts mean. Therefore, I thought, okay, I include a small slide to explain the two concepts. So here on the left-hand side, we see a consistent estimator. So what does consistency means? This means that the estimator converges in probability to the true parameter when the sample size increases to infinity. So yeah, quite a lot of technical expressions. So what you can think of is, if you increase the sample size towards infinity, then in the end you will obtain the true parameter. And I mean, it makes a kind of sense, because imagine you have a sample which is a subset of your population. And now you increase the size of the sample towards infinity, then it becomes your population. And then in the end, you actually do not really estimate anymore. So you calculate your model parameter. So this is the concept of consistency, and this is highlighted here. So I know it's quite small, but I tried to zoom in. So I have conducted a small simulation with a consistent estimator for different sample sizes. So here n equals 2 is the red box, and then till the purple where n equals 1000. And here's the distribution of the estimator. So the black line here in the middle indicates the true value. So now, as you can see, if we have a quite small sample size, our estimator on average does not retrieve the true parameter, right? So it's biased, because on average we do not obtain the true parameter. But if we increase the sample size to 1000, then you see the mode of the distribution is above the true parameter. So on average we will obtain the true parameter. So this is what consistency means. But this also means that if we have a consistent estimator, it can be biased in small sample sizes. And this is what methodological research often tries to investigate. How do consistent estimator behave in small sample sizes? So to see whether the bias is large or negligible. Then on the right-hand side, we have an unbiased estimator. Unbiasedness means if we take the mean of the estimator, then we obtain the true parameter. And here you see, regardless of the sample size, on average, we get the true parameter. So all the modes are above the true parameter. So this means unbiasedness. And typically in statistics, we strive for consistent or unbiased estimators because of their properties. So if you need to decide or choose among a set of estimators, then it should be at least consistent. Okay, So now we get a little bit more specific. How can we obtain the estimates for the composite model studied in CCA? So there are several approaches. So for example, we can use approaches to generalize canonical correlation analysis like MAXVA or MINVA. So there are a lot of approaches. Several were developed by Horst Kettenring. Then we have regularized general canonical correlation analysis proposed by Tenenhaus. And then I would argue the most famous one is the iterative partially square algorithm, so developed by Hermann Wold. Or we can use generalized structured component analysis as well, as proposed by Wang and Takane, or also by Glang in the past. But yeah, Wang and Takane make it more prominent again, I would say. And of course, we could also use maximum likelihood estimator. So currently there's no maximum likelihood estimator developed, but in general, so for composite models, but in general also maximum likelihood estimators are conceived. So what you should not do is use the maximum likelihood estimator that was proposed for the common factor model or the reflective measurement model to estimate the composite model, because then you will come up with biased estimates because the estimator is not designed for that model. But if the maximum likelihood estimator is designed for the composite model, then it would also work well. And then what we can also do, if we do not want to estimate the model parameters, or the weights at least, we can use predetermined weights. So for example, unit weights, if we have absolutely no, or if we want to weight them equally, or we can also ask experts about their opinion and use weights proposed by experts. So that is also an option. Yeah, this was step number 3. Now we come to the last step, model assessment. And model assessment in CCA consists of 2 steps. So the first step focuses on the overall model fit of the specified model. And the second step focuses on the assessment of the emergent variable itself and their corresponding parameter estimates. So why is overall model fit assessment important in CCA? Because we specify our model with regard to a specific theory from which we think that it describes the reality to a certain extent. And then our model represents that theory. Investigate whether our theory can be falsified or is falsified or not. And yeah, like in structural equation modeling, there are actually 2 ways to assess the overall model fit. So one is our tests for exact model fit, and the second way are fit indices. And these are 2 non-exclusive ways, so you can apply them both in parallel, so to say, to see what their outcomes are. In CCA, originally we proposed a bootstrap-based test to assess the null hypothesis that the population variance covariance matrix of the observable variables equals the model implied variance covariance matrix of our observable variables. So this is our null hypothesis that we want to test with the test for exact model fit. So we say in the population, our model is a perfect description of the world, so to say. And to do that, we proposed a bootstrap-based test, which was originally developed by Beran Srivastava and is also known in the SEM literature as Bowen-Stein bootstrap. And we proposed it in combination with various discrepancy measures. So for example, the SRMR, which is, I guess, the most well-known measure, but we can also use other discrepancy measures like the geodesic distance or the squared Euclidean distance. So I don't to go too much into detail how they work, but all 3 of them have in common that if the distance between the two matrices is 0, if the two matrices are equal, then all these three discrepancy measures are equal to 0. And if they are not equal, then all these three discrepancy measures are larger than 0. So this is important. How does the bootstrap works? So here we have the distribution, in that case of the bootstrap distribution of the SRMR under the null hypothesis that our model is a perfect description of the world, so to say. So that sigma theta equals, and then as common in statistical testing, we need the critical values. Here they are indicated with HI95 and HI99. So HI99 is the critical value that corresponds to the 1% significance level, and HI95 is the one that corresponds to the 5% significance level. So this is the distribution. Here we have the critical values. And now we can consider the value of the geodesic distance or the SRMR or the squared Euclidean distance based on our originally estimated model. And then we compare that value to the critical values. And if the value of the SRMR for our estimated model is below the critical value, we do not reject the null hypothesis. If it's above, we reject the null hypothesis. So if it's above and we reject, then we obtained empirical evidence against our specified model. So then the model we conclude that the model does not perfectly fit the population. So, or yeah, it's not a perfect description of the reality. Okay, so then on the other hand, we have fit indices. So why were these fit indices proposed to structural equation modeling? And the reason for that is that the test for overall model fit or for exact overall model fit is often regarded as too stringent. And this is due to the fact that, yeah, which goes back to Bock's famous quote that all models are wrong. So we cannot expect that a model is a perfect description of the reality because all models are wrong. And therefore, yeah, proponents of fit indices argue that it's only a matter of the sample size that gets rejected if you apply the overall test for model fit. And to overcome that issue, they proposed approximate fit indices. So here, similar, we have the SRMR for composite models that was proposed by, in my paper together with Jörg and Theo. And also recently, there was the goodness of fit index proposed in a paper of Zhou et al., which will appear soon. So for composite models, of course, these two concepts were developed much earlier for common factor models, but yet now they have also been proposed in the context of composite models. So what do the two fit indices have in common? So they quantify the degree of misfit of your model, but they don't make statistical inference. So it just says, looking at your sample and your estimated model, then you get a value, and the larger the value, the larger the misfit of your estimated model. But we do not draw conclusions about the underlying model. So does our model fit in the population, so to say, done by the fit indice. And this is also the reason why fit indices have been criticized a lot in the past, because they are descriptive and not inferential. So that's, yeah, so you can only make statements about your specific sample and not about the population that you are studying. And the second problem is, because now you have a value, and what people often want to do is they want to know, is my model, does it show an acceptable fit, right? And therefore they need certain cutoff values. And the problem with these cutoff values is that they are subjective and in a certain way also arbitrary, because usually these cutoff values are derived by simulation studies. And of course, the design of your of a simulation study affect the value of the threshold, of the cutoff value. And it's very, very unlikely that the design of the simulation matches the design of an empirical researcher. And then, yeah, you can run into problems because now you kind of compare apple and oranges to each other. And that was also a critique mentioned. But yeah, I don't want to dive too much into that topic because it's a little bit out of scope. And then we have also, next to the overall model fit assessment, so when we regard our model as acceptable or the fit of the model as acceptable, we consider the estimates or the estimated model parameters to see whether they align with a researcher's theory. So, and in doing so, we look at the value of the estimated parameters. So does it make sense? The range of the sign of the estimates. So do they align with our theory, what we expect from our theory? And of course, also at the significance of the estimates. And then if we have employed an estimator, or if the weights estimates suffer from can suffer from multicollinearity, we can also consider criteria that help us to judge whether multicollinearity is a problem for our estimates. So for example, the variance inflation factor. So this is particularly important if you use mode B to estimate a composite model, because mode B weights are affected by multicollinearity, and therefore you should also check the variance inflation factors, particularly if you observe strange values for your estimates, or when estimates are not significant, also you expect them to be significant, then it's wise to investigate the variance inflation factor. Yeah, before I come to the demonstration of CCA, I also, there was also a little bit confusion created by Herr et al., who published recently a paper in JVR, where they dubbed the measurement evaluation steps of partially square structural equation modeling also CCA. This is a little bit problematic because now there exist two methods with the same name but with completely different purposes. So therefore CCA and the measurement evaluation steps are not the same. So that is something you should take away from my presentation. And yeah, I've also written an article about that in the Review of Managerial Science, where I juxtapose the two and to see what are the differences and what are the differences between the two. I don't want to go too much into detail here. What I wanted to say is the main difference between the two methods, I would say, is that in CCA CCA aims at assessing composite models, while the measurement evaluation steps, as the name already says, aims at confirming reflective and formative measurement models. So in CCA we have no measurement because we use CCA to model forged concepts and not theoretical or behavioral concepts. We do not want to measure, or we don't measure because forged concepts do not exist in nature per se, and therefore measurement is not a very useful approach to operationalize such concepts. In general, make sure if you use CCA that you refer to the right approach. So because now we have two approaches with the same name. So if you apply our approach, then make sure that you cite Schubert et al. 2018. And if you use the measurement evaluation steps, perhaps it's even better not to refer to CCA and just call them measurement evaluation steps known from partially square structural equation modeling. So then I come to the demonstration of CCA. And I prepared a small empirical example of tourism research where I consider the concept of value of destination experience. So I found an article of Lee et al. 2018 who published their study in Asia Pacific Journal of Tourism Research. And there they focus on value of destination experience. And I have also here a small quote from the article. Also, there's one more second order construct for the perceived value of destination formed from a scale measuring functional, social, and emotional value. So from that, I derive a new hypothesis or a new theory, so to say, that of destination experience emerges from functional, social, and emotional values within its environment. Because keep in mind, a forged concept depends on its environment. So in contrast to theoretical concepts, which we assume they exist and therefore we can measure them, so you can regard them isolated. But for forged concepts, they need to be embedded also in your theory in a network, because they are context specific, or they depend on the context in which you study them. So therefore, here I have this added sentence within its environment. And what is the environment here? So the environment of value of destination experience in this example is service experience satisfaction, travel experience satisfaction, and tourist happiness. So this is the environment of VDE. And now we can go through all the steps of CCA. So imagine this would be your theory. And now we first need to convert our theory that we have in mind into a statistical model. So this is step one. Therefore, I specified the following model. So here we have our forged concept, VDE, which is now represented in the statistical model as an emergent variable highlighted by the hexagon. And VDE is formed by 3 values. So functional, social, and emotional values, which were in the original study measured via a reflective measurement model. And then here on the right-hand side, environment of VDE. So service experience satisfaction, travel experience satisfaction, tourist happiness. So these are these 3 variables. And as common in CCA, all the emergent variables and the variables not forming the emergent variable are allowed to freely correlate. Therefore, we have here this bidirectional arrows, so highlighting correlations among the variables. Similar for the components of VDE, they are also allowed to be freely correlated. So that was step one, converting the theory into a statistical model. Second step is ensure model identification. So we need to check first, before we do the estimation of the model, that our model is identified. And for that purpose, we apply the 2 conditions that I mentioned earlier. So we need to fix the scale of each emergent variable. So here we have only one, so VDE. And as I mentioned before, the scale is automatically fixed by PLS if you apply PLS. So therefore, first condition is fulfilled. Second condition is no emergent variable is allowed to be isolated in the structure model. This is also the case here because VDE correlates with all the 3 other variables here on the right-hand side. As a consequence, our model is identified. Then, this is the first part. Then, we want to estimate our model, and therefore there are various software packages available. So here in that webinar, I use Adanko. But you can also use non-commercial software packages like our package, or like the package that I developed together with the PhD students, pls-sem. So that you can also use. Of course, you can also use Smart PLS, VAR PLS, Seminar developed by Dunks and co-authors. So there are various packages available, but I've chosen Adanko here. And now I briefly need to change my screen.
Hey guys, if you think you are getting some value out of this video, please do not forget to hit the like button and also subscribe to the channel. I would also appreciate if you can share this video within your social networks or within your networks of people that may need this video. Going back to the video.
Okay, so I did is I transferred the model to Adanko. Yeah, let's start from scratch. So here is our emergent variable with its 3 components. So the 3 different values. They form the value of destination experience. And important is if you use PLS, then make sure that you use mode B. So in Adanko you have to set it to emergent variable. And then as weighting scheme, you need to choose mode B. And yeah, the rest here can be ignored. Then on the other hand, we specify the environment of the forge concept. So these are the 3 variables here because yeah, they are actually, I simulated the data. So I took their construct correlation matrix and generated the data so that I have the same variance covariance matrix of the constructs as published in their article and the same sample size. But yeah, I do not work with the original data set because it was not publicly available. And yeah, therefore these 3 constructs are now modeled as single indicator constructs. Here it doesn't matter whether you use latent or emergent variable, because if you have only a single indicator or a single observable variable, the 2 are the same. So then you cannot distinguish between share of variance that is explained by the latent variable and variance that is explained by measurement error. So the construct is equal to its indicator in the end, if you have a single indicator construct. So now we have a small problem because, yeah, as you mentioned, in the model specification that I showed, we had here this bidirectional arrows, right? The issue is that Adanko is, so at least the current version, in the future it will be revised, but in the current version it's designed to apply PLS path modeling, which involves a structural model. So therefore you cannot specify double-headed arrows, so correlations among the constructs. Like for example in covariance-based software packages where it's quite common. But we can use a small trick, in particular if we allow all the constructs to be correlated. And what does that mean? We create a saturated structural model. So what I did is I draw all possible arrows without creating feedback loops. Meaning I connected VDE to SES, to TES, and to TH. Then I went to SES and connected it to TES and to TH. And then I went over to TES and connected it to TH. So now we have a saturated structural model. What does it mean saturated? So there are no restrictions in the structural model anymore. So therefore, it is the same as a situation where all our constructs are allowed to be correlated. So therefore, although the picture looks here a little bit differently compared to the slides that I showed previously, now we mimic the situation where all the constructs are allowed to be correlated. So that was the first step, specifying the model. Then we also ensured that the model is identified, so I already explained that. Then in the next step, we want to estimate the model, and therefore we click on the Run button. Then, yeah, we have here some settings for the PLS algorithm. I recommend using the centroid scheme in that case, but in the end it does not really change the outcomes. And important is that we check here the box use bootstrapping and use assess model fit. And then we can set a seed to get again, if we run it again, the model to get the identical results, because it involves bootstrap, which is affected by randomization, so to say. And if we set a seed, then we fix the random number generator. Okay, then I set the number of bootstrap samples to 999, and then we can click save and run. So what can we see now? Not much happened. Some paths obtained stars highlighting the significance level. Not that interesting for us because we are not interested in direct effects among the constructs because we allow them all to be correlated. Then we click on the results. So I think now I need to change again. So now now here you can find the results of the estimation. So here are some general notes. 191, this was the sample size, also as in the original study. Then here we get a small figure of the model again. So this is exactly the model that I specified. And then important for us is the assessment of the overall model fit, or the outcome. And here we have the values of the 3 discrepancy measures. So DULS is the squared Euclidean distance that I also mentioned on my slides. So this is the value. And here on the right-hand side, we have the critical values. And as you can see, all the 3 values are below the critical values. Therefore, we do not reject the null hypothesis that the model exactly fits. So of course, this is not a confirmation of our model, but we do, because we cannot, with statistical testing, we cannot confirm our model, but we have not obtained empirical evidence against it. So this is perhaps also important. So it's not a proof that our model is correct, but yeah, there's no evidence against our model so far. So this, and with regard to the test for overall model fit. As you can see here, there are 2 tables. For CCA, they don't matter that much, but Adanko provides the output for the model with a saturated structure model and for the actual estimated model. And as you can see, because I created a saturated structure model, the 2 results are identical. Otherwise, if I would, for example, omitted a pass in my model, then the 2 would differ. But so far for CCA, that does not matter. Then what we can also look is at the SRMR, for example, as a fit index. And yeah, we have some rules of thumb. I mean, we can look at the paper of Cho, which is in press, for example. They recommended, I think, if we have a sample size above 100, a value for the SRMR of 0.08, like Hu and Bendler for factor models. So therefore, this seems to be also fine. So we have no evidence against the fit of our model. So we regard the fit as acceptable. Then in the next step, we want to look at the parameter estimates, their sign and their significance level, whether they match with our expectations. And for that purpose, we go here to Bootstrap, because here we get the results from the Bootstrap, which we can use for statistical inference. And there's a column, weights and t-values. So these are the t-values for the weights. And if the absolute value of the t-value is larger than 1.65 roundabout, then the weight is significant on a 5% level. So, and as you can see, all weights are significant. Now, important for emergent variable, usually we expect weights that are positive because we want to compose something in a negative weight. Yeah, it's quite strange to interpret if we think about a definitorial relationship. So therefore, have a look at the weight estimates. And here we have the weight estimates. I mean, we already saw them in the figure, but they are all positive. And which aligns with my theory that VDE is a concept that emerged within its environment, and it's formed by these 3 values. And then finally, what one could do, which is unfortunately not possible in Adanko, neither in SmartPLS or other software packages designed for conducting PLS, is looking at the correlations among the constructs, because here we have no inference about the construct correlations. So therefore, yeah, we cannot follow that step. But for example, if you use CSEM, you could do that. So there in CSEM, we have much more flexibility for the analysis, but yeah, in the commercial software packages, we are limited to the functionalities implemented by the developers. So therefore, that's not possible. Yeah, and I would say that was it. So what we don't need to do, because I also read the question on Facebook, is what about reliability, for example? So do we need to assess reliability? If you think about the forged concept, it does not make much sense to assess reliability, because reliability is connected to measurement, right? So reliability means if we measure at point 1, we measure again at point 2, we measure again at point 3, we get more or less the same results. So here we don't measure, therefore, reliability is not applicable. I mean, one could think about discriminant validity, for example. So can we distinguish the constructs in our nomological net? But the problem is currently, this cannot be done because the HTMT assumes also a reflective measurement model, right, and not a composite model. So in general, I would argue the idea is applicable. Can we distinguish the constructs from each other? But not with the current statistics that we have. So as you can see, there are a lot of opportunities to contribute to CCA and develop concepts known from factor analysis, which are very tied to measurement theory, to forge concepts and emergent variables. But I would say at that step, we conducted the CCA, we obtained no empirical evidence against our theory. So the weight estimates so far are in line with our expectations. And of course, then, the whole empirical research does not only focus on the statistical part, right? So you need a nice story, you need to derive a well theory, and so on. But that was not the purpose of that exercise. Okay, that was it.
Thank you, Florian. This is very good. I think this would make it very clear to many people who are applied researchers. And then I was thinking to ask you if there's any paper that you would recommend. Of course, you have a few papers, right, that people can look into for this CCA. But I also see that your paper in JBR has a full annotated example, an application of CCA, like a demonstration. So that is something people can look into if they want to apply CCA.
There's one. We are also and we are planning, or we have also some other papers with some examples under review or briefly before submission. So there will be more examples in the near future. And so then of course you can, it's not published yet, but the book of Jörg Henseler that I mentioned on the slides, there you also find some examples. And I mean, I can also provide you the slides if you want. And then
I think that would help.
Because there are also, for those who have no access to a Danko, because I mean, there's the trial version, which provides a lot of functionalities, but not all of them. But there are also added some pictures of how to specify the model and so on. And then, the researchers can use other software packages to which they have access to replicate the analysis if they want.
That would be great. I think that would help a lot. I have a few questions also. The other one is where you showed decision tree, right? And this decision tree showed common factor model is something that exists in the world, that's already there. And then composite model is a forged one. It's something that we create. Researchers use different things to create, right? Then what about some very common variables, like let's say service quality, okay? So service quality exists in the world, like it is something that exists, that we know that, But on the other hand, it may not be something that exists. It may be something that researchers created because there was no concept of service quality like 2,000 years ago, right? Like somebody.
But I mean, it's also about what do you think? What is quality, right? So do you think quality exists in the world so that you can measure it? So, for example, if I look at a specific service, so does it has the specific quality regardless of whether you measure it or not, or is the quality created? And I mean, I would argue that both ways are fine depending on your research question, right? From which way you tackle it. So you, for example, you can say, okay, this component, they define quality. Then you should use a composite model. But on the other hand, you could also say, I have this and this and this and this indicator, they measure the, then you can employ a reflective measurement model. So therefore, I would argue it depends on the type of research question and understanding, and of course also observable variables available that you want to use to operationalize such a concept.
Okay, yeah, it makes sense. Okay, so this is perfect. The other question that I have for you is that in the figures that you showed, right, like this one figure in that example, you not only the nomological network where you connected the composite variable with the other variables, but also you created correlation between all the variables, right? So you show the correlation.
Yeah.
Is it necessary to have that, or is it something that authors?
No. So nice question. So no, it's not necessary to have correlations. So perhaps I can share my screen again to refer to the slide. 1 second. So I guess you refer to, for example, that figure, right?
This figure, or the one in the example that you showed, you know, from Lee et al.
Or that one?
Yes, yes.
So yeah, in general, you don't need to allow all the constructs to be freely correlated. But if you have no prior expectations, then I guess it's a good start to allow them to be correlated. Okay. Because otherwise you would introduce certain restrictions. And I mean, if you have some theoretical arguments for saying that SES and tourist happiness, for example, are uncorrelated for whatever reason, then you, of course, you can also restrict the correlation between these two constructs to 0. In theory, if you apply PLS, then it's not possible, because in PLS you are not allowed to, or you cannot introduce restrictions on the construct variance covariance matrix. So therefore, if you apply PLS, it's not possible. In general, it's possible. And therefore, I would argue also for CCA, it's possible. And then it rather depends on the estimator you use, whether it allows it or not. Okay, perfect. So this is good. There's another question that I have for you, and this is from my own experience. Okay, so I was working with my my master's student. He is developing a scale. He is actually developing an index for smartphone app functionality. So when we were doing that, now of course the variable, the final variable is a higher order construct, but it has like 2 levels of operationalization. So he has like the main variable, the emergent variable is called functional value. And that functional value has 2 dimensions, and then each dimension have multiple sub-dimensions, right? So when we did the first step, the model fit was not very good. This is the step when we are all looking at indicators only, right? Yeah, but without the higher order. Yeah, without the higher order. But then we move to the second step with the sub-dimensions. Now there is some good results. Then we go to dimensions, then the results are better. And then when we go to the emergent variable, then it's all perfect. Do you think that's something okay, or? Yeah, I mean, then if the first, because I've also written a paper about that with the second order construct and with constructs, and which is similar to the Van Riel et al. Paper, right? Where we proposed a 2-step procedure for testing, and I mean, in your case, you would need a 3-step procedure, so to say. But the idea is similar. So what if I would be a reviewer? Then I would likely criticize that your measurements are not acceptable, because, or not, the measurements are not, they suffer from a certain problem, let's say, because in the first step you have your latent variables, right, and ignoring all the higher order constructs. So what you are focusing on is actually the measurement of your concepts. And if there you face problems, meaning, the test for our model fit is rejected, or your fit measures are, the values of the fit measures are above the recommended thresholds, then I would argue that there you have some problems, and then you perhaps have to rethink your indicators that you use to measure, or yeah, start with a smaller number of indicators measuring your constructs. Yeah, that would be my idea. And then, yeah, the problem is then these problems from the first stage where you figured out that the measurements are problematic, it conveys also to the higher stages, right? Because now you work with scores from problematic measurement models. And then, I mean, you also to be honest, you would also have problems in the follow-up models.
Okay, so then what you mean is that it's very important that the first step should have a proper model fit, and then it should proceed, right? Not the other way around. Okay.
Yeah.
Right. Okay, thank you. All right, perfect. And Florian, then before we go into the example, if you can, like I said, there's a question that many people ask, the difference between reflective, formative, and composite variables in a non-statistical way.
Okay, so in a non-statistical way, so how to decide among these three, right? Okay, so yeah, reflective measurement model I would use if I think about the concept that you study, whether it exists or not. And because this is the requirement that you can measure something, right? So it must exist there, otherwise you cannot measure it. So this might be a brief or a small help to decide whether you want to use the reflective measurement model. Then we have causal formative measurement model, which is actually, I would say a special case of the reflective measurement model, because the causal formative measurement model itself, it's not identified. So what you need is some consequences of the latent variable to identify the model. And these consequences, if you translate it then back to reflective measurement models, are the indicators. Of course, they can be observable or latent, but yeah, in the end, it boils down to a kind of reflective measurement model. But the idea is still the same. So if you want to apply a causal formative measurement model, because it's grounded in measurement theory, then you would also assume that the concept exists and it's causally affected by some observable variables. And there's an interesting article of Aguera Ureta. I'm not sure whether you know that article, where they showed that actually the meaning of the construct is not affected by the causal formative indicators. So therefore, the meaning of the construct is fully determined by its consequences. So actually what you can do is cut off the causal indicators, and the meaning of the construct or concept is not altered. Which creates some questions about causal formative measurement model or formative measurement, I would say. But it's outside the scope of of our talk here.
Sure, it's understandable. But this creates questions, Florian, like you said, right? So initially, like many people who were using PLS, and this Smart PLS was one program that many people started using in the last 10 years, right? And because the way people were identifying models was mainly between formative and reflective, right? This is normally what the trend was. Like, there was not much discussion on composites, at least in the applied research, right?
Yeah.
So now when we have this papers, like you wrote very good papers on composite constructs, and then it clarifies a lot of stuff, but then it also brings questions on what's the role of formative constructs then, because if we have reflective and then composite is actually really what formative stood for so many years, right?
Yeah.
And what's the point of having formative? So I think we can have discussion about it some other time, because you're right, it take a long time.
Yeah, and I mean, but the issue is also that formative and reflective measurement model in the context of PLS is not really well defined, I would say, because, I mean, if people who apply structural equation modeling, I would argue if they think about reflective measurement model, then they think about, where is it? about this model. But this is not the model that PLS estimates, because PLS, regardless of whether you use mode A or mode B, it creates a composite.
Right.
So therefore, yeah, and this is also what I criticized in my 2020 article, that because now you in some of the guidelines on PLS you read, yeah, use reliability like Cronbach's alpha, HTMT, average variance extracted, all these statistics to assess, yeah, conversion validity, discriminant validity, and so on. But the problem is, of all these statistics, they assume that model underlying. So, and now you use an estimator that produces biased estimates for that model, and then you plug them in the statistics, right, to calculate the statistics. So you use the loadings here, which are actually no factor loadings, they're composite loadings. And then you calculate the average variance extracted, for example. And yeah, then the question is, what are the results? And I mean, in the appendix of of my paper in Review of Managerial Sciences, there also show that it's problematic and that you can come to very strange results or misguiding results. And and interestingly, this, I mean, I'm not the first to criticize that. So Rönke et al., they wrote, I don't know, 3 or 4 papers about that, but it was not really yeah, well heard by the community. And so that's one point. Another point is that Ed Rigdon, he developed another view on modeling. So he developed this holistic construct framework, which can also be where he argues that in the end you can employ the composite or a common factor to represent the concept in your statistical model. So this is just a different underlying, so to say, philosophy. So depending on which, I fully understand it. Now it becomes a little bit confusing because there are different philosophy. I mean, we have scientific realism, we have constructivism, pragmatism, so anti-realism. So there are different strands of philosophy in sciences. And depending on the philosophy or on your worldview, you can apply statistics with a different meaning. And the same apply, so you can, there are different, there are various problems, and some can be overcome by your philosophy that you follow, I would argue. And but if you stick, for example, to scientific realism, I would argue it's quite difficult to employ PLS to estimate reflective measurement models. Okay. Because this is not what the estimator estimates.
Perfect. Thank you. Once again, thank you so much, Florian. I mean, I'm sure that I learned a lot from your presentation, and it clarified a lot of issues that I had. I'm pretty sure that others would agree to this. So thank you so much. Okay.
You're welcome, and thank you very much for the invitation. And we keep in touch, right?
Of course, yes, we do. Thank you so much.